And we'll set up the slideshow to be from the current slide. And let me hit these last two announcements. I know the first one really has no purpose to you at all, but you may know of someone that you need to share this with, as in maybe someone you're tutoring or you know. Tomorrow, Wednesday, the 30th of November, the last day to withdraw from fall term, either full term or second mini-term classes. Tomorrow is the last day to withdraw. And a withdrawal does not hurt you academically at all. It doesn't reduce your grade point average. It doesn't do anything. The only thing academically it might do is put you further behind before you graduate, but yeah, that's it. The biggest potential problem, which is not a big one, is financial services, financial aid type thing. If you've already withdrawn from a class or made a D in a class or made an F in a class, and you draw from the second time, then you can, they won't pay for you to take it. You can still take it. It doesn't hurt you academically, but financial aid won't pay for a third time. And the other thing, should mention this too, with financial aid nowadays, there are term limits. They only pay for so many terms. In the past, you could almost go, it seemed like indefinitely. But now, so there is that other little factor there too. But it's far better to withdraw than to make a bad grade. Bad grade goes with you, it hurts you, and you have to take the course over anyway. So why have it hurt you and you take it over,
You just take it over
with no consequences. Okay. Now, the second thing is this one. The student course evaluations are now open for fall term. So anytime you can, you've got a bunch of them to do.
Well, I have to evaluate
Yes.
3 times.
Yes, exactly. Well, you're doing the course more than the instructor. The instructor is part of it.
Yeah, there's like a part on each of them for the instructor.
Yeah, instructor too, so whatever. I might be a better linear algebra instructor than I am a Cal 3 instructor or differential equation, something like that. So I don't know.
Probably will, just because, my mood may change as I go through.
See.
Oh yeah, he's great. You know what?
Not so good. Okay. All right.
These things too long, start to get a little crazy.
Thank you very much for that endorsement. Okay. Any questions before we get started? Did you find one you wanted to question or? Okay. 38. Oh, okay. Back there. Okay. That was 1.138. I was on the page and I forgot we had said that. Okay. In these problems, verify the indicated pair of functions is a solution for the given system of differential equations on the interval negative infinity to infinity. And this is page 11. Whoa. Okay.
That one actually isn't as good as
exercise.
Don't you think? Maybe 23 or one of those groups would probably be better.
It's up to you.
Because this one is using a pair of functions. This one's using singular functions or family.
Okay. You want to do one of those?
Yeah.
Pick one.
Let's do 22.
So, which one?
22.
22. Okay. Number 22. Now this is an interesting one because one of the functions is in with an integral as its solution. So that means you would have to have a numerical thing, but we can still do it. Okay, it says verify the integrated family of functions is a solution of the given differential equation. Assume an appropriate interval I of definition for each solution. Okay, number 22. Here is the differential equation. dy dx plus 2xy is equal to 1. There's your differential equation. You want to verify that this y equal e to the minus, e to the minus x squared times the integral from 0 to x of e to the t squared dt plus c1e to the minus x squared. Okay. You want to verify that is a solution of that differential equation. Okay? Well, we know what y is, so we can plug that in here. We know what x is, so we can plug that in. It's just x. Okay? Okay? What we need to find is what dy dx is.
So we just subtract that whole thing over, plug in y?
Wait. Do dy dx. Right? Yeah. Okay. Now, all right. For that first term, looks like a product rule to me. Would you say? Okay. So what would it be?
Well, you're talking about e to the negative x squared.
E to the minus x squared.
I took the derivative of that.
You did? Well, you aren't through then, are you?
It would be 2x up front.
Negative 2x out front. So let me scrunch in some so I can do that. Negative 2x e to that. Then you're multiplying it by this one. Okay. Plus.
We leave the C1 there.
Second.
Be 2C1 x.
Okay, wait. Let me write down the first one, right? E to the minus x squared. Now you're doing the derivative of the second one, which was, and what did you say?
Oh, yeah, we have the next product. And that'd be
E to the,
t squared.
no, x squared.
Oh, yeah.
Okay. All right. And I think I know what that is. Well, we'll go back and evaluate in a minute. Okay.
Well,
Plus.
it's like
All right.
x concept is 0.
Yes, exactly. Okay. So e to 0 is 1. So this is 1. Right? Okay. All right.
And then this would be
Wait, let me. I think I'm okay. Yeah. I was going to erase, but I decided not to. Okay. Oh, yes, I was going to erase. Okay. I knew I had to erase something here. Okay. And what's that be?
negative 2x.
Negative 2. I'm going to put my C1 in there too.
C1
X.
e to the negative x squared.
Got it. All right. So now we use that and what our knowledge of x is and what our knowledge of y is and see if we get what we have. Okay. Say again?
It's going to be kind of gross. It's kind of
It's just long, but not bad.
That's what it means.
Minus 2x e to the minus x squared times the integral of 0 to x e to the t squared dt plus 1.
That was the hardest term to write.
Yes. Minus 2c1 x e to the minus x squared. That's my dy dx.
Plus 2.
Plus 2
I would
x
get 2x.
e to the minus x squared times the integral of 0 to x e to the t squared dt.
I thought it was dt. Oh, yeah.
I'm sorry.
You got it. I just heard you wrong.
Okay.
Plus C1 e to the
Okay. Let me go on and write the 2x in there too, plus 2c1x e to the minus x squared.
y.
Okay. Well, it's 2x times y.
Oh, yeah, okay. Yeah, I was
So
gonna.
2x times the first plus 2x times the second.
I was gonna put it in parentheses.
In parentheses,
so
that would have been fine too. I was just, yeah, sorry.
I see what you're doing now. I was like, are you? Because at first I thought you were taking the derivative of it, and I was like, why? But you're not.
Okay.
Equals 1.
Yeah, that's the question. Does that equal 1?
Well.
Let's look at this term here. There's a minus 2x e to the minus x squared integral 0 to x e to the, and here's a plus 2x e to the minus the integral. Those two add to 0. And then we have a minus 2c1 x e to the x squared and a plus 2c1 x e to the x squared. Those add to 0, and 1's equal to 1.
That's beautiful.
Thank you. You said it was going to be yucky.
I was just talking about the length. I wasn't talking
right,
about
right,
the operations. I was worried about running out of line space.
I'm used to that too. I usually do. That's what I manage to squeeze in.
I'm sure I can figure that out.
Yeah.
Because before with the whole having to use fee and all that, there was a lot to be assumed from the example that I was trying to go off of.
Yeah. The one big difference in this one is in doing the dy dx, you have to do that implicitly in that equation that you have there.
What you mean?
Huh?
What you mean?
Well, the first thing we did here was find dy dx. So the expression they gave us here was y is equal to blah. Then finding dy dx was easy. Here they say verify that this expression, which is not set equal to y, and it's very difficult to set it equal to y. So what you have to do is take the derivative of that expression with respect to x, and that's going to give you an implicit solution. Dy dx, you find it implicitly. When you do dy dx, or d by dx of the first term, that's just going to be 2 times x minus 5, right, in parentheses. But then you'll have a plus 2y times y prime, and then equal to 0, okay? Solve that for dy dx, and then once you do that, then you plug that answer back into this one, and put your y. Now the good news here is, you see, you can solve this one up here for y squared. You can't solve it for y, but you see all you need is a y squared there.
Yeah.
So that's what you put in there. Okay? Yeah. All right, good deal. Any others?
Not that I know of, yes.
Okay.
Did about half the testing.
Okay. Well, anytime we can come back to it.
What page are we on now?
We're on page 154, section 4.5, example 6. We got close, but didn't quite finish. I think I was in here by myself, and it was it was one of those days that was very cold in the room, and I was clogging up like crazy. I think I had to stop once or twice just to go clear my head because it was pretty bad. It wasn't. I hadn't had a big class like I had before, and it was really, I wasn't as well dressed. I mean, as heavily dressed as I am today. Okay, example 6. Determine the form of the particular solution for this. Okay, we had done the complementary solution. We had done the operators, okay, and we got down to the roots of the auxiliary equation, and I think we found what they were, okay? So I guess what I'll do is this. Here's the original function, y double prime minus 2y prime plus y is equal to 10 e to the minus 2x cosine x. Okay. Now, the complementary function, how do we go about doing that? You do the homogeneous one first. Set that equal to 0 and do that one just like you would have done if that was a homogeneous equation. Okay. Got it? Remember? And how you do that is, this is a linear differential equation. So you do e to the, I think they used mx, wasn't it? Yeah, I'm pretty sure it was, because that gave you m squared and blah, 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 blah. This is back in the previous section. No, it's the section before the previous section, because back when we did, yeah, the auxiliary equation, yeah, you make the assumption y is equal to e to the mx, top of page 133.
Yeah, I remember.
Yeah, okay. So we first do, and this is called the complementary function. That's the one for the, you do y double prime minus 2y prime plus y equals 0. And for this we assume y is equal to e to the mx. So this will be m squared e to the mx. Do I need to go through and do each of it? Okay. Minus 2m e to the mx plus e to the mx equals 0. E to the mx can never be 0, so you can divide that out, and that gives you m squared minus 2m plus 1 equals 0. Do we have any roots? One is m minus 1 squared.
Right.
That would be m equal 1, right? M is equal to 1. But it's a double root
Yeah, it's a double root
at positive 1. So what we do to accommodate that is do y is equal to, and this is where they put in the constants, c1 e to the x plus c2 x e to the x. Remember, if you have multiple root, you have to put the extra x in front. Okay, let's see if I can find that easily. What page were we on before? That was 3.1. Was it 3.1? No.
Auxiliary equation, we were in 4.3.
4.3. Yeah, I'm sorry, I turned too far back.
Distinct roots, two distinct roots, yes. So there's two, then you C2 x e to the.
You see it?
Yes.
Okay, yeah, okay. So that's your complementary function, the one for the homogeneous equation. Okay. Now, what we do, we now consider the right-hand side with the operator that we have on the left-hand side. Okay. So you go back to what they call to equation 7, which is on page 150. Okay. Now, these are the annihilator operators. Okay. When we have one, and you see there's 3 types they give us. Equation 3 on the bottom of 149, if you just had, just had a d to the n, then it's just power functions. Okay. If you had e to the x's and e to the something alpha x and x e to the alpha and powers of x times e to the alpha x, then your differential operator d minus alpha to the n annihilates those. But when you have something that's like this, it has e to the somethings and cosines or sines something, then you have to use an annihilator that's like d2 minus 2 alpha d plus alpha squared plus beta squared. Okay, what's your alpha and beta? The alpha is in this case, your minus 2 is your alpha, and your beta is your 1. Okay, the alpha is the minus 2 and beta is equal to 1. It's the coefficient of the x part. Okay, so from that we know our operator needs to be d2 minus 2 alpha. Well, alpha is minus 2, so it's minus 2 times minus 2 is plus 4, right?
Right.
D, and then plus alpha squared, which would be positive 4, plus beta squared, which is 1. 4 plus 1 is 5. Okay. So that's the annihilator that will annihilate the function on the back there. Okay. So that's why they say that. They say from 7 with alpha equal negative 2, beta equal 1, and n equal 1. Okay, now the n here was that raised to what power? Well, where does the n show up below? That's your power for your x's. Well, you have no x's here. So your n is equal to we have x to the 0 because there is no x in here. So n minus 1 is 0. Looking at example 7, equation 7 on page 150. Your n minus 1 is 0, right?
Right.
Okay.
It wouldn't be 1, but n minus 1.
Yeah, n minus 1 is 0, so n has to be equal to 1. So that's where they got n equal 1. And that's just the power of this thing, and so it's 1. We're not going to worry with it. Okay. It's done for. Okay. So then we have this being our annihilator. Okay. And that's operating on this thing. And that better be a 10 there. No. Oh, okay. They forget about the 10. They just operate on the parts that have x in them. E to the minus 2x cosine x. Yeah. And I can't tell you for definitively why they don't include the 10. It's just a multiple. We're just operating on that part. Okay? and we want to set this equal to 0. Okay? And then the solutions for this side, then, and the solutions for this side will then, you know, supposedly make it work for you. Say again? I'm sorry.
It'll work out.
Yeah, it'll work out. Okay. Okay. Now, so this, applying this operator to 7 then gives you, here's the part that they just, let's go back up here and do this in operator notation as well. Okay, this right here, this part here, operator notation. This would be D2 minus 2D plus 1. Okay, right? That's what this is. Okay. Now, so basically what you're saying here is this operator, and by the way, this is equal to this thing here, right? Okay. Now, so you're saying this thing operating on this thing. Now, again, it bugs me. They leave off the 10 and just pretend it's not even there, okay? But this is this thing operating on Y. That is your left-hand side here, okay? So this is saying, and this is your right-hand side, except for the 10. It bugs me. They just ignore the 10, okay?
I guess they just include it in C's later on.
Second.
I guess that they just include it in C's later on.
Yeah, I believe that's exactly what happens. But it seems like to me you could throw it in there. Maybe it just makes it messier, and it would make it feel better. But anyway, so anyway, this is what this is equal to. So this thing, D2 plus 4D plus 5, operating on this thing, which is exactly what that is, D2 minus 2D plus 1 times Y. Now that has to be equal to 0. Oh, I'm sorry. Yeah. I was writing faster than I was talking. Okay. Thinking. D. Yeah. All right. Now. Okay. That is what we've got from, this is what we got from our annihilator. And then you plugged in what this was without the 10, and that's this, okay? And that's equal to 0, okay? Now, what we have to do is solve these two. They look like quadratic equations, don't they? They're operators, but we treat them as if they're quadratic equations. So we, I don't think there's any way to solve that first one except quadratic formula. Only we're doing it on operators. D is equal to, remember how that goes? Minus, yeah, okay. Here, oh, you know what? I forgot to mark you here.
Oh, hey, thanks.
Yes. You're here and Victor's here. Thanks for coming in. That way you both get counted present. If you hadn't come in, he wouldn't have been here. Okay. So minus 4 with that quadratic formula. Minus 4 plus or minus the square root of 16 minus 5. 2, right? And this yields minus 4 plus or minus the square root of 4, or negative 4, right? 16 minus 20 over 2, and this would be minus 4 plus or minus 2i, right, over 2, divide out a 2, okay? So this gives you minus 2 plus or minus I. I wanted to put a caret over it thinking it was, it's not a
unit vector.
Yeah, not a unit vector. Okay. So that's your two solutions for that D. We already know what the two solutions for this D is a double root of 1. So this one yields D is equal to 1 and 1. Okay. So it's a double root there. So that's where they came up with their roots of the auxiliary equation. This is now called the auxiliary equation. Okay? Now, so your final solution, y, okay, I'm going to cheat big time. It's this one, c1 e to the x plus c2 x e to the x. Okay, that was from your complementary function, the homogeneous one. Now we add to that the solutions we get here. Okay, now remember our 1 and our 1, that's what we used to get these. So you don't have to do them again. Those C1 and C2s can incorporate that. Okay. So that's why you don't have to write it down again. Okay. So that gives you your first two coefficients, because we got 4 on this one. Okay. So your third one, the C3, okay, comes from, now here we go back to, I should have noted these somewhere. Let me think which, okay, we could do anything. 3. Was it 2? So let me just check. I remembered exactly what it looks like. I just don't remember which section it's in. That's too far. This has to be here in 4. Let me find it. Those are those. It's when you came up with the eyes. Oh, here we go. 4-3. Okay. Yeah. See, case 2 was our repeated real roots, which we just did. We had already done it. It just incorporates it. When you have complex conjugate roots, conjugate complex roots, I like to say complex conjugate roots, okay, then your final answer for that one is C1, okay. Now, here's the part that sort of gripes me some, but it's not too bad. It's using alpha and beta, but they're not the same alpha and beta necessarily that we had before, except they are. Okay, look at that. Your alpha is the part that went with the E, and the beta is the part that went with the argument of the cosine. Okay? Yeah, except now we have a -1 as well. So the alpha part is still -2. So basically from equation 8 that you have there, you can do C3 e to the -2x, okay, cosine x plus C4 e to the -2x no, sine x. Wait, let me see. Yeah, sine x. Okay, because your complex conjugates, the plus or minus with the I part gives you your cosine and sine. Okay. So yeah, that's your solution there. So you get the y is equal to C1 e to the x plus C2x e to the x plus C3 e to the -2x cosine x plus C4 e to the -2x sine x. Okay. Now, basically, the -2 goes in here and there on the e part, and the plus I goes in here, and the minus I goes in there. Okay. Basically, is how that pans out for you. Okay. Now, the particular part of the solution is this. This is the one that pertains to the right-hand side, okay? So this is yp, y sub p, and this part here is your y sub c. And your final solution is yc plus yp. The yc came from the homogeneous part, the yp came from the particular solution, the thing on the right. That function of x that had no y's in it. All right. Now, want to do example 7? Sure. Okay. So, all right, to erase this, y'all need it up a little longer. Okay. All right. Determine the form of the particular solution for this one. Y triple prime minus 4y double prime plus 4y prime, I left a y there, 4y prime is equal to 5x squared minus 6x plus 4x squared e to the 2x plus 3 e to the 5x. Okay. It says determine the form of the particular solution for that. Okay. Now, all right. What they do here, with sort of no, okay. All they're doing is looking at the right-hand side. They're not looking at the left-hand side initially at all. Okay? That's your complementary side. Okay? So looking just at the right-hand side, we see that to get the x squared and the x terms, okay, that was 4-3. Is that 4-3? No, that was earlier in this section. That was equation 3. The differential operator d to the n annihilates functions that are power functions. 1, x squared, x cubed, x minus n minus 1. Okay, and since this is going to x squared, that's your n minus 1. 2 is equal to n minus 1, so n is equal to 3. So d3 is going to annihilate those two terms. Okay, so that's why they say d3 operating on these two terms, 5x squared minus 6x, is going to equal to 0. It annihilates it. It sends it to 0. Okay. Now the next term is your d minus alpha to the nth power. Okay. And again, your n there is one more. In this case, n is equal to 2, n minus 1 is equal to 2, so n is equal to 3 again. Okay? But this is for the next operator, which is your, okay, that's, this 2 is your n minus 1, this 2 is your alpha. Okay? So for this one, then you have d minus 2. Okay, if I copied the problem right, did I? Yeah, okay. D minus 2 operating on 4x squared e to the 2x. That's going to make that equal to 0. Okay?
Is the d minus 2 raised to the third power?
Yeah, I'm sorry. D minus 2, yeah, to the third power, yeah. Operating on the, and again, okay, here again, aggravating as it is, they leave off the coefficients. Okay, the 4.
Oh,
Yeah, they leave off those coefficients, okay? They only deal with the functions, not the coefficients of the functions, okay? And if they said why that is, I missed it. I'm sure they must have said it, but I missed it. In the example they gave, example 1, that's just d4, okay? The next one, that's straightforward too, d plus 3. The next one has a, no, they have the coefficients in there. So I don't know, they just threw it there, and they've been consistent in ignoring them.
On page 151 on the term of coefficients, may or may not account for that.
Okay.
It's like in the next few examples.
Okay. So, but then the third one there, it's again that same operator, except it's now to the, you notice there is no n. This is x to the 0. So n minus 1 is equal to 0, n is equal to 1. Okay? But your alpha here is equal to 5. Okay? So for this one, you have a d minus 5 to the first power operating on e to the 5x, and that's equal to 0. I don't guess I need the parentheses there. So that's how they get the, oh, I'm on the wrong page. So I'll say, how did they get that? Okay, that's equal, yeah, d minus 5 to the 1 power e to the 5x equals 0. They left off the parentheses. I was going to say I put them in unnecessarily. I was used to having more terms there, but let's see. Yeah, they left them off here too, so let me go and erase that too. But on the first one, they had to have it in because it's a polynomial. Okay. So anyway, these are your three annihilators. Okay. So that, okay, going back to the first now. Okay, this side is d cubed minus 4d squared plus 4d is equal to this thing over here. Okay? Now, and then you could, okay, and by the way, this is all operating on y, okay, and these are all operating on y, these operators too, and so if you combine them all together, it's your D3, I'm writing them in the same order they do. I'm not really sure why they chose to do this order, times D minus 2 cubed times D minus 5 times D cubed minus 4D squared plus 4D, all operating on Y, excuse me, is equal to, sorry, is equal to 0, sorry. Okay, now, and then they turn around after doing that and just eliminating this part. So I asked myself, why did they ever put it in the first place? Okay, that was taken by the complementary solution. Okay, because you already know that operating on y is going to be 0 because that's how you got it. So then they come back to just these three. Okay, so what are your roots here? D equal, I don't know, I hate saying D is equal to 0, but that's, they just say the roots are 0, 0, 0, okay, for that one. And then you have a 2, 2, 2 for that one. And then you have a 5 for that one. Those are your roots of that auxiliary equation, okay? Now wait a minute. Why do they have 5 2's there? Did I leave that off? Oh, it's to the 5th power. Did I write something down wrong? Okay. Oh, I'm sorry. I'm sorry. They didn't do away with that. They factored it. Sorry about that. This factored as a d times d squared minus 4d plus 4, okay? And this happens to be d times d minus 2 squared. Okay, so I'm sorry. I misread it. I was just looking at it too quickly. I'm going to put those back in a minute, but I need to write the next line down. So this has d, and there's a d, so that makes it d to the 4th. And this is a d minus 2 cubed and a d minus 2 squared, so that's d minus 2 to the 5th. And then this is the d plus 5, or d minus 5. Okay, that's equals 0. The roots for this one are 0, 0, 0, 0, 2, 2, 2, 2, 2, and 5. That's where they get those extras. 4 zeros, 5 2s, and 1 5. Okay. Now, okay. Your complementary solution, by the way, remember you got from here, and this was just d times d minus 2 squared. Remember? Factor out 1. So those came from there. Okay. And this is the part I was saying, so why do them, you know, since you're going to separate them this way? So in my mind, I was trying to do it the way they did, which factoring that, and then they come and give you this solution, okay? And this is your general solution. Y is equal to, okay, for the first d, that's a constant. That's just C1, okay? Your second 0 is plus C2x, okay? Your third 0 would be plus C3x squared, and your fourth 0 is plus C4x cubed. Okay? That accounts for the 4 zeros. Okay? Your 2's, okay? That, remember, is plus C5 e to the 2x, because that's what that one, the alpha was for your e's. That's your first 2. C6 x e to the 2x plus C7 x squared e to the 2x plus C8 x cubed e to the 2x plus C9 x fourth e to the 2x. Those are your 5 2's. 1, 2, 3, 4, 5. And then your last one, yuck, plus C10. Okay, and that doesn't have an x in it, it's just e to the 5x. Okay, now, this is the part I say, why do they do it? They go back and say your complementary solution takes care of this one and the first 2 of these. Okay, those were all your complementary solutions, so you can incorporate the others into that. So your particular solution, yp, and that's what they're asking for here, would then be what's left here. C2x plus C3x squared plus C4x cubed except that, sorry, I knew they were going to do something strange here, and this is what it is. They no longer call them C's. They've changed them to A's, B's, and capital letters, okay? AX plus BX squared plus cx, that's a capital C, cubed, plus d x squared e to the 2x plus e x cubed e to the 2x plus f x fourth e to the 2x plus g e to the 5x. Okay. Now, I guess you have to do the complementary in there first, so then later you can take them out. My thought was, why don't you take them out to begin with? But that would have messed you up, because if you had done that, you might have started this with the constant.
So that was your y of p just then. So your y, so c would be c1 plus c5 or c5 e
Right.
squared x.
Yeah, when you did just this one, you would have had a C1 plus this one plus that. Those would be, no, I'm sorry, this one plus this one plus that. Yeah. So those can incorporate the coefficients that you would have had in here. Okay, group those together, and then it's the ones that are left, and that would be this one, this one, this one, this one, this one, this one. So they were just looking for a particular part. So you do have to list the complementary part with it too. And this was really bizarre because they factored to be just the same as what your annihilators were, except for the annihilator had a 5, d minus 5 that you didn't have here. But then you let what would have been part of this one, the ones that are similar to your complementary solution, you let those go with that. And then your particular solutions are the ones that are left. It's a strange way to express it, but that's how I do. Because the linear combination of corresponding, okay. Remaining terms gives the form for a particular solution. For your convenience, the method of undetermined coefficients can be summarized as follows. Now this is the annihilator approach. Okay, I don't know if this is helpful or not. Okay, Victor, you don't have a book, so I guess I ought to write these down. So let me erase this. This is going to be the summary of our undetermined coefficient, the annihilator approach. The differential equation, L of y is equal to g of x. Now the L of y is that linear operators, because we're dealing with linear differential equation. That's that combination of the operators. Okay? So you have all the y's here, all the x's there. Okay? Now, the differential operator has constant coefficients. Okay? The L of y does. Okay? And the function g of x consists of finite sums and products of constants, polynomials, and exponential functions, e to the alpha x, sines and cosines. Okay, so you can have constants there, polynomials there, exponential functions, e to the alpha x's, sines and cosines. Those are the only things you can allow in the g. Okay, I guess I ought to write there. So the g's include constants, polynomials, exponentials, and that would be of the form e to the alpha x, okay, and sines and cosines, okay, and they would be of, I don't know why they don't mention that, the arguments here are going to be beta x's, okay, that's a weird way to say it, but yeah. All right. Now, when you have that met, here are the steps. Find the complementary solution y sub c. Okay, and what you do that by doing L of y equals 0. Whatever your operator is, the differential operators or the linear differential operators on that, find the complementary solution. Okay, done. And that, by the way, is always going to be in the form of some coefficients, e to the alpha x, x e to the alpha x, yeah, it's going to be something like that. Okay, the second one, 2i. Operate on both sides of the non-homogeneous equation, not the homogeneous, but the non-homogeneous side, with the differential operator L1 that annihilates the function g of x. Okay, so here's what you're doing. You're starting with this L of y is equal to g of x. Okay, and then you operate on both sides with the and this is the non-homogeneous form, with the differential operator L1 that annihilates g of x. So then you have L1 here operating also on this, and the L1 is operating on this. When L1 operates on g of x, it's going to make that equal to 0. It's going to annihilate it. That's why you chose it. Now, okay, the third step, find the general solution of the highest order homogeneous differential equation, L1 of L, well, they leave off the parentheses there, so I will too, of y is equal to 0, okay? Basically, I'm just saying the same thing we did that. The number 2 says operate on them, and I went on and said, and you know that's going to be equal to 0. I probably shouldn't have said that. And I3 says that is going to equal to 0, okay? Roman numeral IV, 4, little 4. Delete from the solution in step 3 those terms that are duplicated in the complementary. The complementary is going to give you so many terms. Delete these terms from your solution there, okay? And form a linear combination y sub p. That will give you y sub p, your particular solution, okay? And that would be the particular solution of L of y equal g of x. Okay. L of y equals 0, that's the complementary part, and the whole thing gives you all the solutions you get here. Delete from these the ones that were up there, and then you get the particular ones here. All right. 5. Substitute yp found in step 4 into the original equation. Match the coefficients of the various functions on each side of the equality. Solve the resulting system for the unknown coefficients of yp. Okay? So in other words, and this is the step we didn't do any of today, you substitute the yp that you got here, okay, into this, into that, okay, match the coefficients on the both sides, okay, until you can figure out the forms. Now, we had done that the last time. I don't think either one of you were here, so you'll have to go back and listen to that. And with those particular solution found in step 5, then you can form your general solution, di y is equal to yc plus yp. Okay. Now, they have remarks here. The method of undetermined coefficients is not applicable to linear differential equations with variable coefficients. They have to have constant coefficients. Okay?
And they get rid of them anyway.
Huh?
And they get rid of them anyway.
Well, only the first one. You know, the others you hang on to them. But those are the constant coefficients on the right-hand side. We're talking about coefficients on the left-hand side. Okay? They have to be constants. Okay? That doesn't work with variable coefficients on the left-hand side, nor is it applicable to linear equations with constant coefficients when the g of x term, the right-hand side, has g of x equal to log x, 1 over x, tan x, and inverse sine x. Okay? And so on. Now what does that and so on mean? That means any logarithmic function, exponential functions, yes. Okay? Power functions, yes. Reciprocal functions, no. Reciprocal power functions, no. In other words, x to the minus power, or x to a fractional power, those don't count. Log x, or any log of x. Tangent x, secant x, cosecant x, those won't work. Cotangent x, okay? Inverse trig functions, they won't work. Only constants, power functions, I said polynomial, they're really power functions, exponential functions, and sine and cosine. Those are the only ones this technique will work. Any kind of function on the right-hand side that is not one of those, like logs, reciprocals, or power functions with exponents being negatives or fractions or decimals or anything else, they won't work. Any trig functions except sine and cosine, they won't work. Any inverse trig functions, they won't work. Hyperbolic functions, they won't work. Don't try anything except those. Constants, polynomial power functions, exponential functions, and sine and cosine functions. Those are the only ones it does. All right. Homework exercises then. Yo! Any of the odds 1 through 9, either 11 or 13 or both. Any of the odds 15 to 25. Any of the odds 27 to 33. And then any of the odds 35 to 63. And any of the odds 65 to 71. There is a discussion problem there. I doubt if that answers in the back, so don't worry with it. All right. That finished 4.5.
With less than a minute left.
Less than a minute left. Where we'll start next time is 4.6, variation of parameters. Okay? What we've been doing is undetermined coefficients. Now we're going to be doing variation of parameters. Okay? Joseph Louis Lagrange was one of the ones who started this variation of the parameter. At least he named it. Okay? Well, I guess he started. He was one who did. So we'll start next time at the top of 157 with a brief look back at linear first-order differential equations. Remember that? Y'all, okay, have we got a minute or not? No, okay. We'll start there. I was going to do a quick review of that now, but we'll do that later. Okay.
And is next week finals week or the week after that?
Okay, we have class this week, and we have classes next week. Okay, finals begin on Friday of next week. So the last day of class is the 8th, I think it is.
So
Today's
next Thursday.
Yeah, Thursday is the last day of class. So we'll have today and Thursday of this week, Tuesday and Thursday of next week. Thursday of next week, I will be passing out to you your final exam. And now, what may happen see, we got variation of parameters, and we have the Cauchy-Euler equation. And I don't think I'm going to do anything in Green's function except maybe introduce it to you. And then it says solving systems of linear by elimination. I don't think if we have time, we'll do some of those. But then I'll give you your Chapter 4 test. That's probably going to be the final exam. Chapter 5 is another modeling chapter. Okay. Chapter 6 is a review of power series solutions of linear differential equations. Not going to do that. If we have time, I'll introduce you to Laplace transforms. That was the one other thing mentioned in the course description that we haven't really hit on. And that's a whole new ball of wax, so you probably won't be tested on it. If we have time, I'll introduce you to it. And we may, because we, like I said, variation of parameters and I think is and Cauchy-Euler. Those are the last two I've ever gotten to. I've never gotten to Green functions. So if we get those two done, I'm going to be a happy camper. I can introduce you to Green's function, maybe a little bit on the systems. I doubt if we'll do much on that, but I may introduce you to Laplace transforms just because, or neither of you are electrical engineers, or those are the people who use Laplace transforms the most. I don't know what the other three people are. I don't think they're electrical, but if they are, then I'll really refer them to read that chapter because that's important to them. I did Laplace transforms and never once since used them. So, but they're pretty handy things. They're really remarkable. But all right, good deal. We will see you on